Alright, silly people, here's the situation. We have a time-independent wave function, which we need to normalize, sketch, um, have it evolve in time, and then find the probability that it's in the ground state, and then find the um, expectation value for the energy in the infinite square well. Um, and we're going to do that all very carefully because there's like 7 integrals in this problem. So starting off, let's just throw together a normalization factor um, by taking the integral of the time-independent wave function with respect to, um, or the square modulus of the time-independent wave function over all space with respect to position, and setting it equal to 1, which is going to be a squared 0 to a over 2. We have x squared dx. We have an a squared from a over 2 to a, and then it's just a minus x squared dx. Set that equal to 1. So the first integral is going to be x cubed over 3, so we're doing that sort of thing. X cubed 0 to a over 2 over there. And then over here, we're going to end up with a minus sign. And also over 3, we're evaluating a minus x cubed from a over 2 to a. So plugging in the bounds, we have a cubed over 8 and a squared minus 3, or minus a squared over 3. The right hand bound is going to evaluate to 0. The other one is a minus a over 2 with a minus sign thrown onto it. So it's, again, it's a over 2 cubed, so it's a cubed over 8. Which means you really have a squared a cubed over 6, no, over 12. Yeah. It's equal to 1. And then a, so the normalization factor is 12 over a cubed under a square root. Awesome. If you want to sketch it, it'll look very much like this Desmos window that I have open right here. So again, a is determining the right bound of the wave function. It's an even wave function where the center is exactly a over 2. Yeah, it's at a over 2. And the peak is at the position a over 2 times the square root of the times the normalization factor. Will give you the peak. So that's what the wave function looks like. So switching back over to the solution, we need to now turn it into a time-dependent wave function. And the way to do that is by taking the sum of n of Cn, and then it's the time-independent wave function times the time evolver, which is e to the minus I e sub n t over h bar, will give us the time-dependent wave function, which means we need to find out what Cn is. Cn is given by the square root of 2 over a times the integral over all space times sine n pi x over a times the time-independent wave function dx. So in our case, we're going to have root 2 over a, And then go ahead and bring out the normalization factor, so 12 over a cubed. And then we're going to have a couple of integrals. The first one is going to be from 0 to a over 2. It's going to be sine n pi x over a times x dx. And then the other integral is going to be from a over 2 to a minus x times sine n pi x over a dx. Okay. First thing I'm going to do is I'm going to split, or well, actually the first thing I'm going to do is going to simplify the prefactor. So it's going to be square root of 24 over 8 fourth. And then I'm going to split up the second integral into two integrals. So it's 0 to a over 2 x sine n pi x over a, and then plus, you're going to have one that's just multiplied by a. You do an a over 2 to a sine n pi x over a dx, and then the other integral is now minus sine a over 2 a x sine n pi x over a dx. So interestingly, this integral is the same as this integral. So to get the form of that, we're going to have to do integration by parts. So it's going to be u, we're going to have u is equal to x, we're going to do du is dx, we're going to have dv sine n pi x over a, which means, and that's dx, which means v is going to be minus a over n pi cosine n pi x over a. Right. Continuing to simplify the prefactor, you'll have like a 2 root 6 over a squared. Let me not make that look garbage. Over a squared, and then I'm going to use parentheses instead now. So the first one is uv, so x, or it's minus ax over n pi cosine n pi x over a, and then it's plus the integral just of cosine, or no, it's plus a over n pi integral of cosine n pi x over a dx from 0 to a over 2. You're also going to be subtracting literally the same result, except evaluated from a over 2 to a, and then you're also going to have one where it's just plus a times, it's going to end up being a over n pi, or minus a over n pi, so I'll throw the minus sign there. Yeah, minus a over n pi cosine n pi x over a evaluated from a over 2 to a. Okay. let's do the integrals that are inside of the brackets now, and also factor out um, a factor of a over n pi, because all of them seem to have that term. So we'll have minus x cosine n pi x over a plus a over n pi sine n pi x over a. And that's evaluated from 0 to a over 2. Again, you have the same exact result, but evaluated at different bounds. So that, except subtracted and at a over 2 to a. And then we'll go ahead and plug in the bounds on the last one. We factored out an a over n pi. So that's going to be cosine of n pi, which is that, and then a minus cosine n pi over 2. Very cool. Alright. Simplifying the prefactor out front to 2 root 6 over a n pi, and then plugging in the bounds for both of these guys. So the first one is going to have minus a over 2 cosine n pi over 2. Right? And then plus a over n pi sine n pi over 2. That's the first term. We have minus a cosine of n pi, and then that's basically minus a cosine n pi, and then plus a over n pi times sine n pi, which is always 0, so don't even think about that term. And then we're throwing in an a over 2 cosine n pi over 2, and a minus a over n pi sine n pi over 2. And then we already have the last bit of the evaluated integrals. So, in an interesting turn of events, we have some cancellation. This will cancel out this. Let's continue simplifying. All these have a factor of a onto it, so we'll go ahead and move that out into the prefactor and cancel out the a on the denominator of it. And they all also, I think, no, they don't all have factors of n pi, so don't even worry about that. It's going to be 2 over root 6 over n pi. We have a minus 1/2 cosine n pi over 2 minus another 1/2 cosine n pi over 2. So that adds up to just being minus cosine n pi over 2. Um, we have 2 times a over n pi sine n pi over 2. We have a plus cosine n pi over 2, and I think that's it. Yeah, that's it. Um, Also, in another interesting turn of events, this will cancel out this. So that's fun. Now we can factor out an additional factor of n pi and also 2. So we have 4 root 6 over n pi squared. Um, and I meant to factor out that a earlier. Yeah, so sine n pi over 2, that is Cn. And we can plug this in now to our wave function. So again, the time-dependent wave function is the sum over n Cn psi x0 times exp minus I e n t over h bar. Plugging that in, we have 4 root 6 over n pi squared. And then we have the normalization factor, so 12 over a cubed under square root. We have the sum over n of, oh boy, there's a couple of different there's a couple of different ones. So both of them are going to have sine m pi over 2. Both of them are going to be multiplied by exp minus I e n t over h bar. But depending on what part of the domain you're in, it's going to be either multiplied by x if you're in the region between 0 and a over 2, and it's going to be multiplied by a minus x in the other region. So I'm just going to, I don't need all of that. Copy this down for a over 2 to a. Put a little curly bracket on there. Fantastic. We can simplify and plug in some definitions of these functions. So sine n pi over 2 happens to have a couple of different values. Interestingly, it's equal to 0 if n is even, because at that point you'll just have sine n pi, which is always 0, and you have a minus 1 to the n minus 1 over 2 if n is odd, right? So we can use that definition. We can also use the definition of the energy states for the infinite square well, which I don't remember that off the top of my head, so I'm going to go grab it from what I wrote down earlier. That's the energy states for the infinite square well. So let's plug all of that into the time-dependent wave function then. First, I'm going to simplify the prefactor. So we have 4 times the square root of 6 times 12, which is, what is that, 72? Over n pi squared. And then you still have a square root of a cubed. So I'm going to write it like this. 4 over root 72 over a cubed. Right. Sum over n sine, well, we're doing the substitution for sine, so it's -1 and -1. I don't know why the n pi squared isn't in the sum. It should really be in there. 4, and then -1 and -1 over 2 over 4 can be over pi squared. This can be over n squared. And then we still have the x, and this is supposed to be a minus x. We got x, we got exp minus it over h bar times n squared pi squared h bar squared over 2ma squared for the first range. Second range, I don't know why I'm going to write it all out again. Copy that John down. Except now you're multiplying by a minus x instead of just x. It's looking really gross now. From a over 2, whoops, a over 2 to a. Let's keep simplifying. So 72 is not a perfect square, but we can factor out a we can factor out a 4 at least. So it's going to be 8 over pi squared, and you're left with, on the inside, 18 over a cubed. Sum over n, minus 1 to the n minus 1 over 2 over n squared times exp. Let's simplify the exponent. So one of the h bars will be canceled out, and that's pretty much all the simplification we can get. So pi squared h bar over 2ma squared. That's multiplied by x. That's from 0 to a over 2. And I think that's about as simple as it gets. Sorry if you were looking forward to a pretty wave function. That's just what it is. And it's supposed to be a minus x for that region. Yuck. Okay. Now there's still more to this problem. We need to find the probability that the state is in the ground state, which is very simply the square modulus of C1 squared. And we already know what C1 is, or we know what Cn is anyway. It's this stuff here. So plugging in for 1 and squaring it, you'll get 4 over root 6 over pi squared sine pi over 2 squared. Absolute value of sine pi over 2 is 1. Um, so we're actually just squaring this, so it's just 16 times 6 over pi fourths, which is, what is that? 16 times 6, that's 96 over pi fourths. That's your probability that you'll be in the ground state. If you wanted to put it into an actual fraction, 98%. 98% roughly. That's pretty cool. So let's keep going. We need to find the expectation value of the energy, which is given by the sum over n square modulus Cn squared times the energy. Makes sense. So plugging in our stuff, we'll have the sum over n of 4 root 6 over n squared pi squared sine n pi over 2 squared. And then using our definition of the energies, which is n squared pi squared h bar squared over 2ma squared. The absolute value of sine squared of sine n pi over 2, I guess, I think it's just 1, so that's okay. So we're doing the sum over n of 1 over, it's 96 over n fourth pi fourth times n squared pi squared h bar squared over 2ma squared. And then simplifying that a bit, 96 over pi squared sum over, and then let's even pull the rest of the prefactor out, h bar squared over 2ma squared. And then it's the sum of 1 over n squared, where n is odd, which is a known arithmetical series, which is given by, what is that, pi squared over 8. Simplifying again, 6 divided by, what is that? Okay. 96. Come on, computer. 96 divided by 8 and also divided by 2 will give you 6. So it's 6 h bar squared. Pi squareds will cancel out. So 6h bar squared over ma squared is the expectation value for the energy. Okay, long problem.